Okay, so welcome back for round two of my discussion of this pure tone oscillator that I put together based on the biquad or state variable circuit, which I will include the circuit of along with a brief derivation of the basic concepts of this circuit because it's a bit hard to understand without any context. Now, before I get into that, I just want to briefly show you guys that this enclosure here has been so successful that I decided to make another bigger one in the exact same style here with a rod that hooks on a piece of plate stock. Can't even really get this on camera. It's a bigger box. It's going to end up being 2 bolts. And I don't really have anything to put in it yet. I think maybe I'll put together a harmonic distortion analyzer or something like that. But I haven't dressed up any of these welds or anything yet. It's just tacked all the way around. You can see the heat affected zones from the tacks along the back. And the bend on this front plate I did exactly the same way as the other one. What I did was I scored it with the angle grinder in a really straight line. And then I just bent it, and it bends only a certain angle before it jams, and it can't be bent anymore. And so if that angle wasn't far enough, you could take a little bit more off with the angle grinder, but you get it exactly right. And then I put these tack welds in, and now it's really locked in that angle. It's not going to ever change. And normally when you weld stuff, you have to worry about the shrinking, cooling molten metal reefing on something and changing the effective angle. But because it was jammed, you don't have to fixture it or anything. So I can just go zzz, 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 and I could crank these boxes out. It's really a straightforward process. So for anyone looking to make enclosures, there's some concepts there you're welcome to utilize as you see fit. All right. So, oh yeah, point number two. This is pretty low frequency right now. I'm down at about 20 hertz. I don't know if you can really see it because of the camera, but it's scanning along at a obviously visible rate. So the fact that this thing is stable here and I can go up into the audio range, the actual audio range, that's special. When I first powered this up, that wasn't the case because the amplitude of this oscillator is controlled by LDRs, light dependent resistors. And when their ability to modulate their resistance gets close to the order of frequencies involved in the waves here, the control loop completely shifts character. And so you have to kind of be careful about how you design it to accommodate that. All right, so here is the circuit. And I'm just going to try and hold it stable there for a second so you could pause it and look at it. But make no mistake, I totally know that there's no way to understand this circuit just from looking at it. So for a high level, for someone who's familiar with biquads, this is a regular biquad loop, just with LDRs in the timing resistors, and another LDR in the damping loop. So that's great, but it's pretty unlikely that you can really see what's going on here. So when I first powered this up, I'm picking off one of the sine waves, sending it through a diode through a 1K to drive an LED that modulates this damping resistor. But at low frequencies, that was causing me a huge problem. So there's another one that goes to the other sine wave, the minus phase sine wave. So because I only had one LED, I had to drive it through 2 sides like this, and that got it stable to half the frequency, and the variations in the amplitude were hugely crushed by this, but not completely removed. So I did come up with a system and later revised this and completely removed any low frequency dependence. I'm really quite pleased with that. So, but anyways, in order to understand that, we'll have to look at a simpler biquad. And before I get into that, I want to show you the total harmonic distortion. So I don't have an excellent option uh, for really doing quick and precise total harmonic distortion measurement. But I just fed this input into my 16-bit sound card of my PC and recorded it on Audacity and performed some FFTs. and looked at the relative magnitude of the harmonics relative to the fundamental. Now, a couple problems with the Audacity FFT. I love Audacity; it's a great program, but it the FFT is kind of wonky, and the plotting system isn't really great, and so you got to be somewhat careful about how you look at things because it can hide peaks from you. Sometimes it's automatically set to a 65,000 point FFT, and so if your line width is way thinner. Anyways, I don't really want to get into. Just know that using just your 16-bit sound card, just running the sine wave in, FFTing it, it works, but it's fraught with pitfalls, and so you got to be careful. Okay, so this is a plot of the the wave here. It's at about 1K, and you can see the third harmonic there. And oh, sorry, the second harmonic. It's the third tone, including if you make this one 1. Anyways, but so an issue with this is that I, in order to not be distorting the front end of that of my computer, I had to attenuate this tone by about 30 dB on the front end. Like, so 30 dB less than full scale is where the distortion of the system falls into the noise floor. And then I had to digitally gain this up. So when you just FFT straight from Audacity, you won't be able to see your noise floor. It's really small. If you're like, the noise of this amplifier is lower than the noise of the system. This is the noise floor of the system. Anyways, that digital amplification factor costs me a little bit in dynamic range. So I can only really measure um, up to about, depending on how I do it, this plot isn't the optimal way. I can only really measure about 72 dB below. So below a pure tone. And so, okay, this is the oscillator set to, um, I have a trim pot that controls how damped it is. And there's a range of stable settings. This is on the hot side, and you can clearly see it's the third harmonic sticking out there. So that, I don't care about that. I'm interested in when the oscillator is set as cold as it can be stable. So just that's the basic plot. Here is the device set cold, and I've truncated this FFT, but I made notes here that hang on, let me make sure I'm framing this. Oh man. So okay, so I got a tone that is registered as minus 6 dB from full scale, and it's digitally gained up. So anyways, and then this, where that third harmonic is, and it is visible. It may not be clear in this particular snapshot, but if you watch it for a while and you do averaging and stuff, you can see that that third harmonic is 72 dB down from that. So that equates to about 0.025% distortion off the top of my head. You check my math on that. But anyways, that's pretty good. I spanned the capability of my sound card but it's because it's a sucky sound card, and within 30 dB of full scale, it's really hugely distorted on its own. So okay, anyways, that's that. Um, in order to understand this circuit a little bit better, for those of you who haven't seen any of this stuff before, I just want to show you. This is what I call the second law circuit. It's Newton's second law, um, but it uses voltages to represent the state variables. And so this is where the state variable filter name comes from. So that I use a summer, and so a bunch of voltages make currents sum together. We're going to treat that as the sum of the forces. So this node is the sum of the forces. And then I got to integrate that once to get the velocity, the net velocity of a mass. And then I'd have to integrate it again to get the position. So it's a op-amp summing stage and a double integrator with respect to time. Okay, so that's the circuit that can solve Newton's second law. And so if you want to set this up to do a spring and mass system, a spring that bounces back and forth on a mass, the equation for that is that if I displace the mass a little bit this way, it wants to pull back this way. And if I squeeze the spring, it wants to unsqueeze. And so the force is equal to ma still, but it's also equal to minus some constant times the displacement. So this resistor here functions as that constant. I feed the position signal back into the sum of the forces. And so in this case, there's only two forces. There's some applied input, some force I can use to wiggle this mass, and its own motion, its own position creating a force, giving rise to a force. So um, I hope you can find a good spot in the video to pause these slides if you need time to get used to them. It's if you're seeing it for the first time, it can be confusing. So anyways, that's fine. Okay, so in order to get the typical sort of biquad filter, where it's a band pass filter, you have to add some damping. And so in the equation, in order to have damping, like drag, you need a force that is in the minus direction and proportional to the velocity. So in order to do that, I feed some velocity signal into because this is an inverting integrator, it has to go into the non-inverting input to give rise to an inverting force. So this leads to an exponentially decaying signal, and you can set this amount, if this was a pot, you can set the Q of this filter. And so one of the cool things about the biquad is that it gives you a band pass, a high pass. High pass is over here, and the low pass is over here. And so it's a really good filter, really configurable. You can compare the outputs of the different filters and so on. It's really cool. Okay, and so one more point is that if I wanted to have an anti-friction, which is a weird concept, right? Like if I have some resonating system like this, and I want to give rise to a force that causes it to ring up, it's always leading the phase just enough that it's just going to exponentially grow these and not shrink them. Well, I take the velocity signal and I feed it into the negative input instead of into the positive, right? I make this a plus sign here, and that rings it up. And so in my circuit that I just showed you, there's a fixed resistor ringing up the system, and then there's a variable resistor, the photocell, which rings down the system. And so those two interplay depending on the amplitude of the oscillations to keep it in the pocket. So I think that is all there is. We'll go back to the real circuit now with our knowledge in mind. We say that, okay, there's two integrators, and it's in a loop with a summing amplifier. And I'm picking off those two signals to light up which is a sine and a minus sign. If you work through it, you shouldn't, I'm not expecting you to know that, but these are anti-phase. Well, actually, it makes sense because there's just an inverter in between these 2 points, so it's easy to see. But anyways, they drive this LED, which keeps the amplitude constant. And the two timing resistors I've dropped in, you have to vary these two resistors in tandem in order to keep the circuit the same character, but just change the frequency. And so normally I would use a double potentiometer for this, and that would have been better. Like, these take some seconds to stabilize. But this allows me to put in, so the frequency control is just, I'm leaking some current into an amplifier that drives the LEDs, shining light on the photocells. And so I could also inject a current from any source to warble or to sweep or whatever within the limits of these things. And I probably need some kind of servo, some kind of PD loop to get that to be even remotely good enough. So I think I mentioned that this is a semi-serious build. I was just having fun. Like, I've been out of the electronics shop for a little while, and so it was just kind of fun. But this is actually not the current circuit. This is the one that I used for most of it, and it was the easy thing to put together. But I'll show you the revision I made now that you understand this. Okay, so I mentioned the problem where the LDRs, when they respond at nearly the same frequency as the wave itself, that changes the phase of the different terms, and it becomes a much more complicated system because these things have their own latencies, and so they're integrators too. And so you have actually 1, 2, 3, 4, 5 integrators, and all sorts of interdependent couplings and so on, nonlinear. Um, But here's a really good way. This nearly rinses out that effect, but this really rinses out that effect. And I'm so happy with this. This totally blows me away. So what I'm doing is I'm actually picking off two signals. So this is a partial circuit, just the amplitude control loop. And this is the photocell that sets the damping. And so I'm picking off two signals that are actually right angles to each other. They're a cos and a sine of the same amplitude. And that, by the way, that amplitude is 1.4 volts peak to peak. It's about a volt RMS, and it drives these four LEDs, and these are tiny little surface mount 0603 yellow LEDs, and so they sort of act like a squarer, converting a voltage to a photocurrent, where in either direction it's rectified, right? Either direction creates a positive amount of light, and so I have sine squared plus cos squared. So that's a constant. It's not perfect because the LED isn't really a squarer, but it's close enough to a square that this freaking works really well. So, um, yeah, I think that's really all I have to show you guys today. Um, I can't test my lowest distortion of this circuit lower than 72 dB below the amplitude of the tone, but it's clean to that amplitude when I've set it cold, like it's closer to ringing down than to ringing up, and there's a range, right? So yeah, I think that's everything. I hope you enjoyed this little mini lecture. Thanks for watching.